So my name is Owusu, and I'm working with Ashley, Evo, both at UNSW Canberra, and then Sven Buddha at ANU, and Simon Murphy as well at UNSW Canberra. So this morning I'll be sharing with you some aspect of my work I've been working on for the past year, which is using GALAH solar type stars to propose a new method for separating the old and young sequence of these stars in GALAH, in the Milky Way galaxy. So my key takeaway messages are basically two. The first is that one, the elemental balance of sodium, basically which is thought to be synthesized through core supernovae or explosive massive stars, is showing sort of enrichment beyond solar metallicity. So we trying to explain or find out the likely cause of this enrichment beyond solar metallicity, and using the abundance we see at solar metallicity or its enrichment as well. We're also using it as a method to propose a new method to separate the Milky Way's old and young sequence thick stars. So this is just an overview of the Milky Way as we know it. And over here we have a cross-sectional view, and then basically we know the Milky Way is made up of the bulge, it has the halo and the thick stars, basically the thin and the thick stars. And depending on the part of the galaxy in which you look at, the component consists of very different kinds of stars, some old, especially if you look at the bulge and the halo, and if you look at the thin big stars as well, we have extremely high rich metal stars over there for young stars. And over here is also the periodic table, which I assume a lot of people have seen here already. And it just basically shows us the range of elements present in our universe and where they are synthesized from or where they are produced from. A particular reference that I want us to pay attention to is in this particular plot is like the sodium. So sodium is basically thought to be synthesized from the activities of explosive massive stars. And but the current result that we see in sodium, the trend in sodium, basically contradicts this existing knowledge, and we try to explain why that is so. So back to the thick and the thin disk stars. Currently, how these stars are being separated out. If you look at, for instance, the studies conducted by Hedin and Etel 2017, when you look at the elemental balance and against the metallicity of an element for various age sequences, in order to separate or distinguish between the old and the thick stars, a line is just drawn from the point where they are, both stars are presented, and then they use that method to basically separate that. But if you look through the diagram over here on your right, it goes to show that at the intermediate ages, between 6 to 8 gigayears, the separation is basically sort of, there's a huge overlap over here, just around this particular region. And around that place, that point, the thick and the thin disk stars are not well separated, so into their various components. And similar method has also been used by Rico and Blanco 2014 as well, and also Bensley and Etel 2014. Basically, in both of these studies, we see that at very young and old sequence or very young and old ages, there's a clear separation, but within the intermediate ages in both sequence of the disks, there's a huge overlap, and it's difficult to distinguish between both sequences of stars. And the studies conducted by Bensley 2014, it goes on to show that the economic classification of stars due to the low velocity tail of the thick stars will be classified as thin disk stars, or while stars from the high velocity tail of the thin disk stars also be classified as the thick stars. So basically making it difficult to show that there's still contamination around at such ages. And just taking this quote by Dean Hook, who is the founder of the Visa Credit Card, said we need to find a new way of looking at things to create much greater innovation than new ways of doing them. So based on this, I inspired by this, Nissen until 2020 basically published the result whereby they look at solar type stars. And in the solar type stars that they saw, which was around 72 stars within our Milky Way galaxy, within metallicity range of minus 0.3 to plus 0.3 dex, we saw an unusual abundance of sodium obtained in this particular plot over here between intermediate ages. This goes to show that there was a clear demarcation between the two different sequences of stars, basically indicated in their studies. So this particular samples of stars that Nissen basically used, we also have them in GALAH DR3, but unlike the Nissen star that he basically used, which were 72 in number, we have over 6,000 of these sample stars in GALAH DR3. So basically, we took these stars and then we took the selection criteria and selected the stars to have a larger samples to try and replicate the studies that he did. And from over here, which is like the plot over here on the alpha versus the metallicity plot, the metallicity being on the y-axis, x-axis, and the alpha ratio on the y-axis, you see that the solar type star, which is our star that we selected, is basically represented in orange, indicating that it's sort of over. Yes, it falls basically within the thick and the thin distance from the samples indicated over here. So we just did something very simple. What we did was that we selected the samples of stars that Nielsen had basically used, which is about 72, and we in GALAH DR3 selected same samples of stars that is over 6,000 samples. And what we did is that we just overlaid this plot of sodium enrichment on it, which are the thick, the blue over here indicating the young sequence of the thick stars, and the red over here indicating the old sequence of the thick stars. And if we look at the plot on the first column, panel L, you get to see that there's a clear demarcation between those sequence of stars. And we also went on to look at the abundance of sodium against these metallicities as well. And we see that for around 0.3 metallicity dex, we see a high sodium abundance as well for around 0.25 dex as well. And the position of the sun being represented here as just indicated the average age of the edges colored by, and the stars are basically indicated by the color of the median edges of the stars as well. So we did a similar plot for the sodium and metallicity abundance as well, and the metallicity being on the y-axis and the abundance of sodium being on the x-axis, and we bin them according to the various ages. And we see that between the 6 and 8 giga years as well, we have a high abundance between 4 to 6 and between 6 to 8. And these are most of the intermediate mass stars that we see a clear contamination within those particular sequence from the earlier plot that I showed to you. And we plotted for most of the elements present in GALAH DR3, and from there, they'll try to see the elemental balances and to quantify the trend. And the one that is of interest to us is sodium in this case, which is over here. The red stars basically represent the Nielsen data, and the blue stars represent, the real blue basically represent that of the young sequence as well. I'll plot it there. We'll see that for the sodium type stars within the intermediate ages 5 to 6 giga years, we see a higher uptime for sodium. And the likely reason for this is still not unknown. We also try to quantify the trend by fitting a line to between the intermediate ages for the 50th percentile and weighted them by the 16th and 84th percentile to see the spread in each of the data. So the slopes represented over here have been scaled up by a factor of 10 to the power minus 2. So and just a key note to indicate is that sodium still shows around 6.5 giga years, with a high uptime around we see a high uptime of around 0.2 dex in sodium abundance, or the elemental abundance of sodium. So in this plot as well, the ages have also been reversed just to give an idea of that. Okay, if we move towards younger ages, we see the high uptime of sodium continuously showing an increase. And then we also see a new effect, which is just the point whereby there's an uptime just around this point of around 6.5 giga is showing that that's the point where basically sodium begins to see that particular sort of the increase or the overproduction as well. And then the rise in sodium material metallicity for younger stars in this case is unexpected given the existing understanding that sodium is synthesized through core collapse supernovae. But initial results that we basically looked at suggest that the effect of the progenitors of the explosive massive stars could be due to metallicity effect. So the plot over here is just the similar plot that is you have over here, but in this time around, we plotted the error bars in this case, and we see that for sodium still shows that particular increase bit from around 6.5 with the continuous increase in the abundance of sodium at intermediate ages over in the plot as well. So we basically took the use from Nomoto, Woosley and Weaver 1995. We took the Nomoto 2013 and Emoji and Jeffrey 2018 to look at the various metallicity effects for sodium for two different solar mass. And we see that from most of the yields that have been predicted in theory, we still see a continuous increase or like a rise, a higher uptake to a factor of around almost 2 for both sodium for higher metallicity, going to support the fact that indeed the progenitors of the metallicity effect from the progenitors of the explosive massive star is one of the likely explanation for this upturn as well. And then also proposing the new way of separating the Milky Way stick and the thing, this we looked at the various stars, which is the gray over here represents our solar type star. The red over here indicates the thick disk stars from the missing data. And over here, the blue ones, we have the young disk stars from missing data. So basically, we just looked at the thresholds from where these stars are basically separated on our solar GALAH DR3 solar type stars and try to just by eye estimate do a cut for it. So the orange line over here, the solid orange line represents the standardized cut, which is the initial cut that we made. And based on that, we also carried on different kind of cuts to see how the slopes will vary for each of the various cuts that we make. And the results over here show with the age, they are balanced with regards to the age. The slopes indicate that indeed the slopes that we obtain from this particular cut is quite robust. And it shows that this proposed model for the separation of the thick and the thin distance, or the old and the young sequence basically is pretty robust. And so we are writing a paper which is due to be submitted by the end of this month, and to add that to show that at the same age and metallicity and alpha enrichment, sodium is an effective tracer of the young and old sequence of the Milky Way disk stars. And as a way of summary, this is just my take home, and we are still looking at other studies, which is to look at other models to explain the abundance of sodium by looking at AGBUs, which is supported by the work that Julia and the team at Monash are doing to use synthesizers or to model this using the omega plus code to see what the effect of AGB stars will have on the sodium abundance at higher metallicities. Yeah, thank you.
I'll start. Is there a particular reason why sodium should be a good tracer rather than like random sequence of other elements?
Yeah, that was because when we looked at sodium, as I indicated to you, what we saw from this particular plot over here. Yeah, because
it's like empirically, but why is that? What's the reason why sodium is the special element here?
Is this the reason why sodium is a special element is because of the abundance of sodium that we see at higher metallicities, the enrichment at intermediate ages.
Why?
Yeah, is the reason why we have this increase or this overproduction is something that we are still trying to study to understand. But the one of the results I showed to you indicates that the metallicity effect from the progenitors of explosive massive stars are some of the theories that have been proposed to be the explanation for this. Other studies favor the AGB models as a likely explanation for why sodium is showing this overproduction at higher metallicities as well.
Maybe you did this and I missed it, but is it possible to use a combination of multiple elements of a linear combination or something like that to get a better tracer of how to distinguish one from another, like not sodium, but sodium.
Yeah, so one of the sodium is an alpha Z element, and one of the other alpha Z element that we've seen a higher increase in the abundance as well is scandium. So scandium is also something, but we've not done any sort of detailed studies into scandium. But when we look at the various alpha Z elements, sodium, aluminium, and scandium, they all show this particular sort of pronouncement enrichment. But sodium had a more pronounced enrichment compared to the other alpha or odd Z elements. Yes. So if we look at the odd Z elements categories, scandium is one of the likely elements that can also be considered to be used for this particular studies as well. That can be studied, looked further into if it's possible to use that as well. Yeah.